On this video, we're going to do some more practice with our volumes of revolution and the volumes of our known cross-sections. So consider the region bounded by y equals f of x equals 9 minus x squared. That's our green parabola opening down. G of x equals x plus 3 is the yellow straight line. And the y-axis I've tried to make a little thicker, so make sure we clearly understand what the boundaries of our region are. So we're talking about this right here. So first, and we're just going to set up integrals but not actually solve them so we can get more practice. We're going to first in part A find the area of the region. So we can imagine drawing our little differential rectangle here. And our delta area is going to be the base times the height. Now the base is going to be our delta x. And the height is going to be this top curve minus the bottom curve. So I'm just going to write it as f of x minus the g of x. So that's going to be our 9 minus x squared minus the quantity x plus 3. But I'm just going to leave it as that. And so to get our integral, we are going to say that the area is going to be that integral from, and we need to know where these two intersect. So we're going to take 9 minus x squared equal to x plus 3. I'm going to make it 0 on the left side so we can factor this with a positive x squared term. And you can use your box and diamond, or if you know how to guess and check, I think that's going to be x plus 3, x minus 2. So that's going to give us negative 3 and positive 2. Now we're only going to go from, so the points of intersection are going to be at negative 3 and positive 2. But we're going to use the y-axis as one boundary, so we're just going to use the 2. So our limit's going to go from 0 to 2, and it would be f of x minus the g of x, and that would become a dx. So there's our area of that region. Now, the next one we're going to do is revolve it about the x-axis. So if we're revolving around the x-axis, as we spin that around there, if we take our little differential slice, that little rectangle, and we pull it out and then turn it sideways, it's going to be what we call a washer, a very thin cylinder with a hole in it. So this we call a washer, and its delta x is going to be pi times the outside radius squared minus the inside radius squared, and then the height is going to be a delta x. Now that outside radius is going to be the top curve. It's going to be that distance. Let's see if I can pull this down without making you seasick. So it's going to be our outside radius is going to be that distance from the edge of our solid to the axis of revolution, which in this case is the x-axis. So that is our outside radius right there. That's going to be the top curve, which is our green parabola f of x. And then 0 is going to be the axis of revolution. So that's going to be a pi times our f of x squared. And then the inside radius is going to be that distance from the axis of revolution to the edge of the hole. So that's going to be the inside radius, which is going to be top curve minus the bottom curve. And the top curve is our yellow linear one, the line, the g of x. And so that minus the 0 is going to give us g of x squared delta x. So our volume is going to be pi coming outside the integral. 0 to 2 are the limits, and it's going to be f of x squared minus g of x squared and a dx. Now when we revolve around the y-axis, if we look at our little rectangle, we can see that our axis of revolution, the y-axis, is parallel to our rectangle. So that means we are going to use a shell method. So our shell method here means that our delta volume is going to be 2 pi r h and a delta x. Our radius is going to be that distance from the axis of revolution out to our rectangle. That's the x-coordinate of that point on the rectangle. And the height is going to be our top curve minus the bottom curve. So it's going to be 2 pi. X is the radius, and the f of x minus g of x is going to be our height. So our volume will be given by 2 pi integral from 0 to 2 of x times f of x minus g of x dx. Now on the next one, y equals negative 2. Y equals negative 2 is going to be a horizontal line down here. So now when we spin our rectangle around that line, if we spin that around and then pull it out, it's going to look like another big washer. So that washer, so this is another washer. Our delta volume is again going to be pi outside radius squared minus inside radius squared times a delta x. Now our outside radius is going to go from the outer edge of the solid to that axis of revolution, the line of revolution. So that's going to be top minus bottom. The top is the f of x, and the bottom is that negative 2, y equals negative 2. So that's going to be a pi times, and that's going to be an f of x minus the negative 2 squared. And then we're going to subtract from that the inside radius, which is going to go from the edge of the hole to our axis of revolution. So again, I'm thinking top minus bottom. The top this time is our line, which we've called g of x. And again, minus the negative 2 is going to make that a plus 2 squared, and then our delta x. So that will make our volume be pi times the integral from 0 to 2 of the f of x plus 2 squared minus the g of x plus 2 squared, and then a dx. So on the y equals 10, now our line of revolution is going to be way up here at y equals 10. That's above our curve. So as we spin our rectangle around, that is again going to be a washer. We're going to get this thing with a hole in it. So our washer is again going to be pi outside radius squared minus the inside radius squared, and then a delta x. So that's going to be pi times, now our outside radius here is going to be that distance from the edge of our solid, which is now going to be down, whoops, lost and got my eraser up there by mistake. So it's going to be from the edge of the outer edge of our solid to that axis of revolution. That's going to be our outside radius. We're going to make that a top minus bottom. So the top is our y equals 10. That's the 10. Our bottom is that line, the yellow line, which is our g of x. So that's going to be a 10 minus g of x squared minus our inside radius, which is going to go from the axis of revolution to the outer edge of the hole, to the edge of the hole. So that distance is going to be a top minus bottom, which is the 10, that's the top, minus the green parabola is our f of x. So that is going to be a 10 minus f of x squared, and then a delta x. So our volume is going to be pi, whoops, it's my left-handedness getting in the way, pi integral from 0 to 2 of the 10 minus g of x squared minus the 10 minus f of x squared dx. Okay, looking at our line x equals 4. Now x equals 4 is a vertical line, so that is going to be, now this intersects at 3, so x equals 4 is going to be over here. So since our rectangle is going to be parashell to that axis of revolution, we are going to say that we're going to use a shell method. So that makes our delta volume 2 pi r h delta x. So that's going to be 2 pi. Now the radius here is that distance from the axis of revolution to our rectangle. Now in a horizontal distance, we're going to go right minus left. The right is our x equals 4, and the left is the x coordinate of that point. So that makes our radius 4 minus x. Our height is still going to be the top curve minus the bottom curve, and then we'll have a delta x. So our volume is going to be 2 pi integral from 0 to 2 of 4 minus x times f of x minus g of x dx. Now, the line x equals -1 is a vertical line, but it's going to be on the left side of our region. So, again, it's going to be parashell. So we're going to, for the radius, want to go from the axis of revolution to the edge of our rectangle. So we're going to go right minus left, which is going to be the x minus the -1. So let's see, we got another shell. Our delta volume is again going to be 2 pi r h delta x. That's going to be 2 pi. Our radius is going to be x minus the -1, and our height is still going to be the top curve f of x minus the bottom curve g of x. So our volume is going to be 2 pi, integrating from 0 to 2 of x plus 1 times f of x minus g of x, and that'll be a dx. Okay, now we are going to look at the solid formed by taking cross sections perpendicular to the x-axis that are first semicircles. So I'm going to, maybe so I don't have to keep scrolling up and down here, remember that our region is going to look something like, we got the parabola, we've got the straight line, and we've got the y-axis. So again, we're talking about this region right here. Our rectangles look like this, and we're going to imagine now that coming out of this, out of the actual my iPad, your paper, is this semicircle. So if you lay your head down and look, you will see this semicircle, and it has a little thickness to it because it's got a delta x for a width there. So our delta volume is going to be the area of the cross-sectional piece times delta x. And our area is a semicircle, which is going to be 1/2 pi r squared times our delta x. Now our radius, this distance right here, which is a diameter, is going to be this distance, which is our top curve minus the bottom curve. That goes all the way across. So our radius is going to be the f of x minus the g of x divided by 2. So that makes this delta area, or delta volume rather, is going to be pi over 2, and then that's our pi over 2, 1/2 pi. The radius is going to be f of x minus g of x divided by 2 squared times a delta x. So that is going to make our volume. Now when we square that, we can see that that over 2 part is going to get squared as well. So we can pull that all the way outside the integral, joining our pi over 2 to make that a pi over 8. Integral from 0 to 2 of f of x minus g of x, quantity squared, and that will become a dx. Okay, now the quarter circle. Now we're going to, let me see if I can erase this a little bit. So I'll try to bring back our picture in some of its integrity. So here again is going to be our rectangle. And now we're going to imagine you can bring this up straight, and then there's a quarter circle coming out there. So that's going to look something like this. There's our quarter circle, and it's got a little bit of thickness to it. It's a delta x in thickness. So our delta volume is again going to be the area of our cross-sectional piece times delta x. This time we have 1/4 of a circle. That's going to be our area. So that's going to be pi over 4. Now in this case, this distance is the radius, and that's exactly this distance, which is our f of x minus the g of x. So in this case, for the quarter circle, we're going to get our delta volume is pi over 4 times f of x minus g of x squared delta x. So that means the constant that's outside our integral is going to be pi over 4. Isn't that kind of interesting compared to the pi over 8 that we got for the semicircle? Now, if we do an equilateral triangle, so let me see if I can erase part of this again. So this time, let me bring my pen back. Now our little rectangle, we're going to come out of here with equilateral triangles. So it's going to look something like that with a little bit of thickness. These I think are the toughest. They're the most complicated. So our delta volume is again going to be the area of the cross-sectional piece times delta x. Now our area is going to be a 1/2 base times height. That's the area of a triangle. Now when we have this equilateral triangle and we drop in the perpendicular in order to get the height, that makes these into 30, 60, 90 triangles. So in a 30, 60, 90, you may remember, maybe not, that the side lengths go x, 2x, and x square root of 3. Okay, so let me bring my pen back up here. So this distance across here, that is our vertical distance there. That is our f minus g. So this distance here is half of that. And our height is going to be that f minus g over 2 times a square root of 3. You with me there? So that is going to be a square root of 3 over 2 times f minus g. Crazy. I told you this was the most complicated. So we have a 1/2. Our base is going to be our f of x minus g of x. Remember, that's the base of our full equilateral triangle, not the half that we created by putting in our height there. Now our height is going to be that square root of 3 over 2 times f of x minus g of x, and then we have our delta x. So crazily enough, if we gather these constants together, that becomes a square root of 3 over 4 integral from 0 to 2, and again we get an f of x minus g of x squared, and that becomes a dx. Okay, let me slide this up a little. So now we're going to look at an isosceles right triangle with a leg on the base. Okay, this is kind of tough to imagine. Let me see if I can draw this for us a little bit. So here is our rectangle, and we have a leg, so that means this is one side of our equilateral triangle. The other one's coming straight out from there, and our hypotenuse is going to come down there. So I'm going to try to draw that here. So our leg is actually on the base. Another leg is up here because this is isosceles, and our hypotenuse is coming down. And we have a little bit of thickness because of our delta x there. So our delta volume is going to be, again, the area of the cross-sectional piece times delta x. That's, again, a triangle because it's going to be a 1/2 base times height times delta x. Now, the base, this, whoops, didn't mean to make that the eraser. This part right here is exactly what we're seeing right here. That is our f minus g. because it's isosceles, our height is exactly the same thing. And so our delta volume is going to be 1/2, and it's going to be f of x minus g of x times another f of x minus g of x, and then our delta x, which is going to make our volume be, we just have a constant of 1/2 that's going to come out, and once again, we get a f of x minus g of x squared and a dx. So on our last one now, the isosceles right triangle with a hypotenuse on the actual figure. So now we're trying to, here's our rectangle. Now this is the hypotenuse. So as we bring this up out of the board, this is going to be our right angle up here. And the hypotenuse is right here on the actual region. So I'm going to draw that with, here's the hypotenuse that's on the region, still isosceles, but that puts the right angle up here. And so again, we're going to get our little delta x for a thickness. So once again, I'm going to slide up a little bit. Our delta volume is going to be the area of the cross-sectional piece times delta x. That, because it's a triangle, is again going to be 1/2 base times height. In our case now, the base right here, that is that distance right here, which is our f of x minus g of x. So that is our f minus g. When we drop the perpendicular in to get our height, we can see that dropping this in here creates, because this is a 45-degree angle from our original 45, 45, 90 isosceles right triangle. When we drop that perpendicular in, because that's 45, we get another 45, 45, 90, another isosceles right triangle, where this height is going to be the same as that length, which is half of the f minus g. So that is going to make our 1/2. The base is our f of x minus g of x, and our height is going to be that f of x minus g of x over 2, or we can just pull that 1/2 together as part of that constant 1/4 integral from 0 to 2, once again getting an f of x minus g of x squared dx. All right, there's a little run through of all of the different volumes we want to know how to do.